In lesson 4.4, we're going to discuss radical functions. And chapter 4, the whole chapter is mainly about inverse functions. So radical functions are actually inverses of polynomial functions. So we will see that relationship towards the end. Notice here our objectives. We have three main objectives here. We want to be able to graph radical functions. And then linking in with that graphing of the functions is we should be able to determine the domain and range of radical functions. We don't need the graph. We can think through that in a few different ways, but graphing is one way to think through that. And then find the inverse of polynomial functions. But with that, we'll need to restrict the domain of the polynomial so the inverse is a function because we want to work with functions. So let's jump in. Radical functions. A radical function is a function containing at least one variable in the radicand. So the radicand is just the part that's within the radical, within the square root, or within a cubed root. Even here, this, underline it here. Remember, x to the 1/2 is the same as the square root of x. The 2 is the index here, and the 1 is the exponent. So when we have rational or fractions as exponents, it actually refers to a radical function. All right, here's the example. This is going to help us know our our parent function for graphing square roots. So it says graph the square root function. Graph the square root function f of x equals the square root of x, state the domain and range. Whenever we've come across a new function, we usually plug in some values. We can choose some kind of wiser or smarter values. And so I'm going to start with -4 because I see I'm going to take the square root of it, and I know the square root of 4 is 2. However, I did this purposely. The square root of -4 is not just 2, it's 2 times the square root of -1. So we actually have 2i, which right off the bat, that tells us that negative numbers, we can't take the square root of negative numbers in the real numbers. And so we're not going to use negative numbers. So we're going to skip all negative numbers because they will give us imaginary solutions. So let's go to 0. What's the square root of 0? Well, the square root of 0 is just 0. So we have this point 0, 0 on our graph. Let's do the square root of 1. The square root of 1 is 1. So we have the point 1, 1. I'm going to go ahead and put this 2. Square root of 2, if you check what that is, it's about 1.4. But that's an irrational number, so that keeps going on and on and on. So instead of choosing numbers like 2 or 3 or 5 or 6 or 7 or 8, I'm going to choose perfect squares because they're easier to work with. So the square root of 4 is 2. So we have the point 4, 2, and then I'll jump all the way up to 9. The square root of 9 is 3. We have the point 93, and let's see if we can put 16 there. The square root of 16 is 4. And we have this point here. And if we look at our pattern here, we can go through those points, and our graph looks like this. Now that might look a little bit familiar. We have another shape that kind of looks like that, which we'll discuss a little bit later. Let's go to the next one, which I'm noticing as I go along, there's definitely some typos in here. Graph this is not the square root function anymore, this is the cube root function. And I actually have to go back because we were asked to state the domain and range, which is a really important part of this question. The domain, well, we could not use negative numbers. There's two ways we can think through this. We can actually think about the function itself. We can't take the square root of a negative within the real numbers. And so x has to be greater than or equal to 0. And then relating it back to the graph, if we just look at our graph, we can tell that our graph didn't go into the negatives. And then our range, as we think about our range, this function keeps increasing. I know it doesn't seem to be increasing very quickly, but it does keep increasing. And so our range, also the lowest point is 0, so y is greater than or equal to 0. And as the x value gets larger, your y value does get larger, just not at the same rate. So let's come down to the next example. It says graph the cube root function. Again, another typo there. F of x equals the cubed root of x. State the domain and range. Well, I'm going to kind of try to choose wisely here. I can go into the negatives here, and I'm going to use 8 because I know the cubed root of 8 is 2, because 2 times 2 times 2 is 8. But this is the cubed root of negative 8. We can take cubed roots of negatives because a negative times a negative times a negative is in fact a negative. So we can put negatives into cubed roots. In fact, odd roots, we can use negatives. Even roots, like a square root or fourth root, we cannot use negatives. Now, we have the point -8, -2. That's not available to graph on the graph that I gave you. Looks like maybe it would be about right here on our graph. But again, can't fit it on there. Let's go down to -1 then. The cubed root of -1 is -1. Do have that on there. Cubed root of 0 is 0. Cubed root of 1 is 1. We'll go to 8 again. Cubed root of 8 is 2. And the next perfect cubed, so 8 is 2 times 2 times 2. If we do 3 times 3 times 3, it's 27. So we would have the point 27,3. Again, that's not going to fit on this graph that I have, so it would be way out here. But what this graph ends up looking like is this. It should be rounded there. And it continues to grow. It looks kind of horizontal, it's just that it does not grow very quickly. And so that's the cube root function. The domain, were there any real numbers that were excluded? There weren't. So the domain is all real numbers. The range, although it doesn't grow very quickly, it's also all real numbers. So we have two pretty important graphs there, the square root function and the cube root function. We graphed the parent functions here, and so as we move forward, if we have functions that are in square root form, they'd be kind of in the square root family, and they will relate back to this parent function. All right, just looking at functions here, find the function described by the rule h of x equals the square root of x plus 3 when the domain is 0, -3, 1, 4, 6. So this function we're describing only has 5 points, and we're just going to put those 5 points right into the function. So let's do h of 0. Well, we'll have 0 plus 3, which is the square root of 3. H of -3. Well, that's -3 plus 3, which is the square root of 0, which is just 0. H of 1, that's 1 plus 3, which is the square root of 4, which equals 2. We'll finish these other two up here. H of 4, just putting it right into the function, we get the square root of 7. And h of 6, 6 plus 3 is 9, and the square root of 9 is 3. So find the function described. So the function is going to be, it's just a bunch of ordered pairs. I'll list all of our ordered pairs. So we had 0 root 3, negative 3, 0. 1, 2. 4 square root of 7, and 6, 3. And so we described, or find the function described by the rule. So it is those 5 points. All right, on this next section, it says find the domain of each of the following functions. So domain, we mentioned this a little bit before, but when we have a square root function, you cannot take the square root of a negative. Within the real numbers. And so we have a square root here, and really this can't be negative. So in order to find the domain, it has to be 0 or positive. So our domain, and we're going to do some work with this, but really our domain boils down to 4 minus 3x has to be greater than or equal to 0. We don't leave it like that because we can simplify that inequality, and we will do that. So we can subtract 4 from both sides. Negative 3x is greater than or equal to negative 4, and divide both sides by negative 3. And we remember when we divide by negative 3 with an inequality, we must switch the direction of the sign. And so a better way to write domain is x is less than or equal to 4/3. And again, we did that because we cannot take the square root of a negative. Therefore, what's under the square root has to be positive or 0. And the way that we write that is it's greater than or equal to 0. On to this part B. Part B has a cube root. And actually, as we mentioned kind of up here, there was no limitations to our cube root. We can take cube roots of positives, negatives, 0, fractions. And so the domain for cubed roots is all real numbers. So don't lump cube roots or odd power roots in with square roots or even because the domain is just all real numbers. All right, part C. Part C is going to put a couple different things together here. We have 2 things that limit our domain here, maybe 3. But those things are 2 ideas. Going to what we're talking about today is we have a square root in here. A square root, what's under the square root can't be negative, which means it has to be positive or 0. So we can say x minus 1 is greater than or equal to 0, which means x, we add 1 to both sides, x is greater than or equal to 1. That's part of it. But there's something else that's limiting our domain, is that we have a fraction and we cannot have 0 in the denominator. And so from this part, we'll actually change the colors here a little bit. So from this part, we know that x cannot equal 2. In fact, also from the square root's in the denominator, and so this whole thing can equal 0, and so x actually cannot equal 1. And what we want to do is combine these different things. So x has to be greater than, I'm going to rewrite our sign here. Our x has to be greater than or equal to 0 or to 1 because of the radical. X can't be 2 and x can't equal 1. X can be anything else besides those as long as they fit that. And so we're going to combine this. So x has to be greater than or equal to 1, but this says x can't equal 1, and so that limits that. So using these 2 highlighted ones together, we have to say x is just greater than 1. You can't have the or equal to. Well, it also can't be 2. Now, 2 fits in here. 2 is greater than 1, and so we have to put another stipulation on here. So x is greater than 1, but put a comma here, and x does not equal 2. And so that would be our domain for this part C.